All right, welcome everyone. This is Math 111Z, and this is where the fun begins. We are going to be solving exponential and logarithmic equations. This is section 4.5 in your text. All right, let's take a look here. All right, solve 2t. We don't have to raise 2 to get 128. So you can take the log base 2 of both sides. Oh, you have to take it of both sides, sorry. Which cancels that out, and t equals log base 2 of 128. Now you can run through the powers of 2, right? 2, 4, 8, 16, 32, so 64, 128, 1, 2, 3, 4, 5, 6, 7. So t equals 7. Now, if you didn't know this, there's a couple additional ways you could use your technology to aid you in finding this number. You could use the change of base formula here and say, all right, well, that's the natural log of 128 over the natural log of 2. And that would give you the number that you were looking for. You could also solve initially using the natural log, saying natural log of t equals natural log of 128. Bring that t down using our formulas. Divide both sides by the natural log of 2. So you get that. And when you plug in this onto your calculator, I recommend doing it in one line. So you would just take the natural log of 128 divided by the natural log of 2. When you do that, you get exactly 7. If you do it in two lines, natural log of 128, you get 4.85200302, and the natural log of 2, you get 0.693141. If you do that and then you type in, even 5 decimal places here, you get this number, which this, represents your rounding error. So again, it's better, you get exactly 7 if you type it in one line. It eliminates your rounding error. So, this one, now solving for 512. If I keep going here on my list, multiply this by 2, I get 256. Multiply that by 2, I get 512, 789. So t equals 9. Again, this is log 2t, 2 log base 2, and log base 2 of 512. This equals 9. That equals t. T equals 9. Right, let's take a look at this one. All right, so again, solving this equation. Now, a couple of things to do this. These are not the same base. If they were the same base, we could just set the exponents equal, but they are not. So we are just going to take the natural log or the common log, whatever is most convenient on your calculator. Maybe the common log is a little bit better because this is already base 10. So let's do that. It doesn't matter what base you take. As long as you take it to both sides, essentially going to work very similar. So common log of 10, 2x minus 1 equals the common log of 3 to the x. So common log of 10, that's going to come down here. And you get 2x minus 1. And log base times log 10 equals x, bring this x down, times log 3. Log 10 is just equal to 1. So this is 2x minus 1 equals x log 3. Let's get all of our x's on one side, anything with an x on one side, anything without an x on the other side. So let's add that over there and subtract this over here. So I have all my x's on the left log base 3, log base 10, 3, or common log of 3 is just a number. It's like a constant, right? I'm going to factor out my x here. Then I am going to divide both sides by this number right here. I recommend keeping this in exact form until the very end, and then typing this in again in one final, thing. So I would have on my calculator 1 divided by parentheses 2 minus the common log of 3. Close the parentheses, and I get x equals 0.65661. Now, if I wanted to check this, I can say 10 raised to the power of 2 times the answer I just got. So I have 2 times second answer, minus 1, and hit enter. And I get this on one side. Then I'm going to take, on the other side, 3 raised to the power of that number. I'm going to go up and just grab that number on my calculator, which allows me to do that. And I get the exact same answer. So I can check and make sure that my answers are correct by plugging in my answer into my original equation. I mentioned at the beginning that I could have done this same problem using the natural log. I'm going to do that over here real quick. So we've got the natural log of 10 equals natural log. So I'm taking the natural log of both sides. Once again, we're using the property where this comes down. The process ends up being pretty much the same. And all my x's, we'll have to distribute this in. So I'm going to have 2 ln of 10 times x minus natural log of 10 equals x times natural log of 3. Get all my x's on one side, so I'm going to move this over here and move that over there. So we're going to have 2 ln natural log of x, or 10 times x, minus x times natural log of 3 equals natural log of 10. Now I'm going to factor out my x. 2 natural log of 10 minus natural log of 3 equals natural log of 10. And I have x equals the natural log of 10 over 2 natural log of 10 minus natural log of 3. I'm going to type this in to my calculator exactly like that in one line, using parentheses to make sure that I get everything where it's supposed to be. Natural log of 10 divided by parentheses 2 times natural log of 10, close parentheses, minus the natural log of 3, close parentheses, and close the parentheses again for the division. And again, I get x equals 0.65661. All right. Now it says solve the equation in example 2 by taking log 3 of both sides. So if I take log base 3 of both sides, I'm going to have log base 3 of 10, 2x minus 1 equals log base 3 of 3x. Those are going to cancel, and this is going to come down. I have 2x minus 1 equals the log base 3 times log base 3 of 10 equals x. Now 2 log base 3 of 10 times x minus log base 3 of 10 equals x. Let's get all the x's on one side, everything without an x on the other side. So this is going to come over here, that's going to go over there. We're going to get 2 log base 3, 10 times x minus x equals log base 3 of 10. Okay, now what? Well, got to factor out an x again, just like before. Equals log base 3 of 10. And now we divide. Log base 3 of 10 over 2 log base 3 of 10. I've got an extra parentheses I don't really want here. Oh, there we go. Right. Minus 1. Now, this equals x. Now the problem is my calculator does not have a log base 3 button, so I'm going to have to use the change of base formula for that anyway. So I'll use the common log. So this would be the log of 10 over the log of 3 times 2 log of 10 over the log of 3 minus 1. So I would have to type all of that into my calculator. I'll just do this part first, save this as an answer, and then use it. So if I take log of 10 divided by the log of 3, I get just this part right here. And then 2 times that same number. So if I type this in, and I'm going to select this as an answer divided by parentheses 2 times that answer minus 1. Lo and behold, I get x equals 0.656651. All right, so we pretty much have got that all done. All right, so we're going to solve this equation right here with e. Usually the best way to solve these equations is to isolate the exponential first. So we got 3e to the 2t plus 6 equals 24. Now isolate this. There are times when this won't work, and then we'll look at some other strategies for solving these, but this one works out just great. Subtract the 6 from both sides. You get 3e to the 2t equals 18. Divide both sides by 3. You get e to the 2t equals 6. Take the natural log of both sides. Those cancel out. And you get 2t equals natural log of 6. Divide both sides by 2. And an exact answer would be natural log of 6 over 2. An approximate answer is going to be ln of 6 divided by 2. Make sure you put that close parentheses after your natural log if you're using some sort of Texas Instrument calculator. And there you go. All right, let's take a look at our next options. Same idea here. We're going to isolate this. Go ahead and give this one a try first, like pause it, give it a try, and then see how well you do. And okay, hopefully you're unpausing it now, and we're isolating the exponential. Taking the natural log of both sides. Dividing by 3. All right, so t equals exactly the natural log of 9 over 3. And that as a decimal is t equals 0.732408. Always plug this into my original equation and make sure I have it right. 4 times e raised to that 3 times that answer minus 10. Get exactly 26. Right? Continuous compound interest. You will recall from our work in the other chapter that continuous compound interest is principal equals, your amount that you have in your bank, A equals principal e to the RT, right? Here it says the bank pays an interest rate of 5%, so our R is 0.05. Compounding continuously. Initial deposit right here, our P is $1,000. And want us to know how long is it going to take for it to grow to $1,200. 1,200 equals 1,000 e to the 0.05 times t. That means we're going to isolate this e. So 1.2 equals e to the 0.05 t. Take the natural log of both sides. Those are going to cancel. Natural log of 1.52 equals 0.05 t. T then is equal to the natural log of 1.2 divided by 0.05. On my calculator, I get my natural log. (1.2) divided by 0.05. And it's going to take 3.64643 years, which, is 3 years and 8 months roughly. Okay. All right, same idea. Go ahead and check your math here. Go ahead and pause the tape and see if you can answer this question. Okay, let's see how you did. So instead of having 1,200, we're going to put 1,400 there. Starting with 1,000 at the same 5%, which is an excellent interest rate these days, sadly, for just fixed savings. Take the natural log of both sides. I'm going to cancel those out because they're inverse functions. And you end up with the natural log of 1.45 equals 0.05 t. Divide both sides by 0.05. T equals natural log of 1.4 divided by 0.05. That in a year's going to take roughly 6.72 years. You can check that in my work. 1,000 times e raised to the 0.05 times that answer equals $1,400. Excellent. All right, let's take a look at our next problems. All right, the cost of a computer disk storage. So the computer storage and memory are calculated by using a byte as a unit. A kilobyte is 1,000 bytes, and a megabyte is 100,000 bytes. The cost of a computer storage memory has decreased exponentially since 1990. For example, the cost of computer storage over time can be modeled with this equation, where T is the number of years since 1997, and CT is the cost given in cents per megabyte. How much did a megabyte storage cost in 2002? And when did the cost decrease to 1 cent per megabyte? All right, and again, this is in megabytes. So let's take a look at this. First of all, how much did it cost in 2002? Note that 2002 is 5 years. So for T, from 1997. So for T, we're going to put in 5. So our answer for A is 0.07 times 0.48 raised to the 5th power. See how much that cost. And we get 10.7 times 0.48 raised to the 5th power. And it costs 27 cents, rounding to the nearest cent, in 2002. When did the cost of computer storage decrease to 1 cent per megabyte? So we want to find out when this happened. All right, I'm going to isolate my exponential function. So the first thing is I'm going to take 0.01 divided by 10.7, and I get this number. Okay, now I have some choices here. I can take the natural log of both sides. I can take the log of both sides. I'll take the natural log. It's an easy button to access on your calculator. This t is going to pop down. So we're going to have the natural log. And I'm going to write this like this, 0.01 divided by 10.7. That's that decimal. It's just easier to write it like that. And is more exact for right now. You can take the natural log of both. Don't pretend that you can do something to simplify this. You can't. You can't like subtract those two or something. It doesn't work that way. So please keep that in mind. All right, so that's what t equals. So t equals, and I can type this in. I already have my answer here. Divided by the natural log of 0.48. Let's do that one more time. So we have the natural log of 0.01 divided by 10.7. And that whole thing, natural log, divided by 0.48. And I get 9.503. Right. So that is telling me that it's going to be 9.5 years from 1997, which would be 9.5 years. So it is going to hit that in 2006 to the nearest year. It will hit that during the year 2006, halfway through that year. And using this model, how much will it take to how much will it make it cost in 2006? Exactly, at the start, 9 years, not in the middle. Clearly, it's going to be close to 1 cent, right? So let's take that, 9 years from 1997. All right, that's 9 years. So t equals 9. And we're just going to plug 9 into the model. 10.7, 0.48 raised to the 9th equals 10.7 times 0.48 raised to the 9th power is 0.01447. So again, we're right in that 1 cent range, which makes total sense based on the math that we just did. All right. Bacterial growth. All right, so a colony of bacteria doubles its initial population of 10,000 in 10 hours. Assume the function is modeled by this, where this is their initial population, t is your hours, and k is a constant, right? And so find the population at time t equals 0. That's just going to be your initial time, right? Like just think about that at 0 time. If you're starting with 10,000, E, doesn't matter what K is, put 0 in, boop, it's 10,000. So that's 10,000, right? It doubles every 10 hours, right? So T is given in hours, so we know that this is true. 20,000 is equal to 10,000 e to some unknown k times 10. We want to solve for k here. So divide both sides by 10,000, we get 2 equals e k to the 10. Great. Take the natural log of both sides. That cancels. Get natural log of 2 equals k times 10. Solving for k, divide both sides by 10. K equals natural log of 2 divided by 10 is 0.06931. All right, now it says, what is the population at time 20? Now, this is interesting because you could just figure this out. It's given hours. It doubles to 20,000 shouldn't it also double to 40,000? 10 more hours after that. Well, let's find out if that's true. All right, so we're going to plug in go ahead and use the full value of K when you plug this in. So I'm going to take 10,000 times E, my K. I'm going to use the full value. I'm going to use my answer key when I type this in, times 20. All right, let's try that out. 10,000 times E, using my full value, so second answer. I could actually type in, if I don't have an answer key, natural log of 2 divided by 10 times 20, which would just be 2 natural log of 2. That's really great math right here. Okay, so I'll do the calculator. All right, answer key times 20. And I sure as heck get 4,000, which is great, or 40,000, which is what I want. But look at if I type it in like this, right? This is going to cancel with that, and I'm going to have 10,000 E times 2 from this canceling, ln of 2. But know that this can go up here, right? So this is 10,000 E ln of 2 squared, which is 4, which is 10,000 E natural log of 4. Those cancel. So I just have 10,000 times 4, which is 40,000. All right, that's some cool math. All right, so now they want to know when it's going to equal 50,000. That's not going to be a whole number. So let's put 50,000 here. Go ahead and pause and see if you can set this up for a second yourself. Great. Equals 10,000 E to the K, which we had that ln 2 over 10 times T. And now we're solving for T. Divide both sides by 10,000. Take the natural log of both sides. Divide both sides by this. Or multiply both sides by 10 over the natural log of 2. And T equals 10 times natural log of 5 all over the natural log of 2. And it is going to take 23 hours. Great. All right, on this example number 7, we are looking to not solve for an exponential, we are looking to solve for a log, and this is a log base 3. Our strategy here is going to always be to isolate our log variable. So we're going to subtract the 4 from both sides. Log base 3 of x equals 2. And then I'm going to write it from log form to exponential form, and this is really the easiest way to do that. So we go 3 squared equals x, so x equals 9. Here you go. Remember how we wrote that? Again, isolating the log and then moving back. All right, now I'll have you try this one on yourself. Go ahead and pause the video. See what you can do. No cheating. Haha. And here we go. Log 2 of x. I'm going to add 2 to both sides equals 5. And then I'm just going to write it in exponential form. 2 to the 5th equals x, which is 32 equals x. All right, and now we get one that has 2 logarithms. Let's take a look at how we can do that. Okay, in general, like if you have like a log and you can get a log on both sides, then you can basically just raise that power to the base and cancel both those logs. But because we have this 1 over here, we're going to have to use our other properties. And we remember that we said that the log of u times v equals the log of u plus the log of v. So if I can condense this into one log, that's going to be very helpful. So this is going to be log of 2x times x plus 4. All right, and now I am going to raise both sides to the power of 10 because this is a common log base 10. Those will cancel. I'm going to have 2x times x plus 4 equals 10. Now it becomes a matter of solving a quadratic equation. Which we set equal to 0. I'm going to go ahead and divide by 2 to make my leading coefficient 1. Just make it a little easier to factor that. And that's x. This is a minus and a plus in the middle, so it's going to be a plus 5 and an x minus 1. I'm going to have two answers here, x equals negative 5 or x equals 1. I should check and see if both of these fall into the domain of a log. So remember that a log has to be all positive numbers going in. And sorry, this should be a negative 5. It's x plus 5 equals 0 when x equals negative 5. So if this x is negative 5, this would be the log base 10 of a negative 10, and that doesn't make sense. All right, so this is an extraneous solution. But the 1 works, log base 2 plus common log of 2 plus the common log of 5 equals 1. Well, that's the common log of 10, which common log of 10 does equal 1, so that checks out just fine. So x equals 1 is your solution there. Again, make sure you check your solutions. I often get extraneous solutions for these, so make sure you're always checking. Let's pause this one and see how you do. Okay, so we're going to combine this into one log term. And then I'm going to raise both sides to the 10th power. That will cancel that. We're going to get x squared minus 3x equals 10. X squared minus 3x minus 7 equals 0. X minus 5, x plus 2. X will equal 5 or x will equal negative 2. Checking my answers, the log of 5 plus the log of 2 equals 1, and we just verified that that's true. This one would be the log of negative 2. You can't take a negative 2 for a log, so this is extraneous. So that is my answer. All right. Solving equations with the natural log. Works pretty much the same way. So, all right. So pretty much the same process. We're going to get all the natural logs on one side, and all the constants will stay on the other side. We're going to use our properties to combine these two logs. Then we're going to raise both sides to like the power of e, essentially. That cancels that out, and you end up with x over x minus 1 equals e squared. And you solve this the way that you would solve this is just a constant now. I'm going to treat it like a variable, but it's just a constant. E squared is actually, which I can take on my calculator, 7.38, but I don't want to write 7.38 over and over again, so I'm going to leave it like a variable, even though it's just a constant. Right, so what I need to do is distribute that e squared, get all my x's back on one side, factor out my x, and divide by this quantity. So x equals e squared over 1 minus e squared. And now I'm going to plug that into my calculator and get a decimal approximation for it. So e squared divided by, parentheses, 1 minus e squared. and I'm gonna get negative 1.156965. I'm gonna put that in. If I take the natural log right here of this, make sure I did that right. Yeah, it looks like I did that right. If I put the natural log into here, natural log of that answer, right, I get an error, of course, because e squares, because you can't take the natural log of a negative number. So this has no solution. And just gonna check my work here. Oh, but I dropped a negative sign, so that's why I thought that was odd. There we go. That should actually be positive because this is a negative number there. Yep, there we go. See how there's a negative here when I distributed that? Right. So, and when I leave this, I move this over, there's still a negative right here. I dropped that negative right there. That's no good. So this should be positive 1.3. So I was wrong. There is a solution for this. And that's let's go ahead and check it. So if I take the natural log of this 1.1565, does that equal 2 times plus the natural log of 0.1565? So if I do that, and I'll type it in exactly the e squared, the negative e squared. Just to make sure I didn't make any other errors. So when I type this into my calculator, on both sides I get 0.145413 and 0.145413. So I get the exact same answer, so it checks out. So my answer is exactly x equals negative e squared over 1 minus e squared, as a decimal approximation 1.5652, rounding to the nearest 10,000ths. All right, nearest 100,000ths. All right, so same idea here. Go ahead and see if you can set that up without making a sign error like I had before. Again, we're going to combine our natural logs onto one side. And then rewrite them into one natural log. Then take e to the both sides. E to the one is just 1. So, or e, sorry, e to the 1 is just e. So you're gonna have x over x minus 2 equals e. Multiply both sides by x minus 2. Distribute. Factor out an x, or move the x's all to one side. Don't forget your negative there. Factor out an x. Divide by 1 minus e. And exactly x equals negative 2e over 1 minus e. And as a decimal, we have negative 2e divided by 1 minus e. And that's going to be x equals 3.16395. Okay, plug that back in if you want to check it. You can take the natural log of that number on one side. Original equation gives you 1.151. And on this side, take 1 plus the natural log of that number that you can go grab up there as your answer, minus 2. And again, you get the same number, 1.1518. So you're checking your answer by plugging in your expression into your original equation. All right. The cumulative box office revenue for the movie Finding Nemo can be modeled like this, where X is the number of weeks since the movie opened and R is in millions of dollars. Wow. How many weeks after opening was the cumulative relative revenue equal to 300 million? All right, so 300 equals ln x plus 1 All right, so we're going to isolate this natural log. That's what we like to do. So I'm going to subtract the 114 from both sides. Now I'm going to have then I'm going to divide both sides by 78.05. Now I'm going to take e, raise both sides to the power of e. Right. So this will cancel, and I'm going to have this number. And minus 1. So let's plug that in. E, grab that number above that I had calculated, minus 1. X equals 9.79. So approximately 10 weeks. All right. X plus 1. Example 10, how many weeks did it take it to reach 200 million? Let's copy that formula down again. What's it? Again, we're going to subtract that 114. Oh, sorry, that's going to equal 85.7. Minus the 78.05. Or divide, I'm sorry. Divide. Gives you 1.098. Raise both sides to this power of e. It's 2.998205. Subtract the 1 from both sides. X equals 1.998205, which is approximately 2 weeks. Great. All right, and then let me know if you have any questions, and we'll go from there. Thanks so much.